The last important thing that we can do with graphs is actually use them to find areas. The area under the graph. For this particular curve, which is an inverted parabola, there are three main sections where we might want to look at the area, although it doesn't have to be restricted to just that. For example, this section in here, which I'm colouring in, or attempting to, that section there, if that was a garden bed, here's the house, here's a bit of edging, and I want to fill it with soil, knowing the area that that takes up would be quite a useful thing to know. Well, it turns out that we can work that out using calculus. The area under the graph is even more useful than that. Here is an example where I've got a velocity and time graph. This graph is showing the velocity, or how the velocity is changing as time goes on. In this section here, we're accelerating. At this section here, constant velocity, not getting any faster or slower. In this section here, decelerating or slowing down to zero and stopping. So this vehicle is speeding up, driving along at the same speed, and then coming to a stop some distance away. How far away would it be, do you think? Well, we can use the area under the graph to work that out. Here's an interesting thing. Velocity is usually in meters per second, or it could be in kilometers per hour, but I'm going to do meters per second. Time is in seconds. If I multiply meters per second by seconds, I get meters. When you find the area under the graph, that's in effect what you're doing. You're finding out an area. Area is sort of like length by width. Although for this one here, I could use the trapezium rule to find this area. If I find this area underneath using the trapezium rule, I'll find the distance that's been travelled by this car. The area under the graph is the distance for this car. If we use calculus, we can find out even more complicated areas. This area here that I'm shading in, because this is again a velocity time graph, would be the distance travelled by this vehicle in the first 1.5 seconds. To find the area under the graph, we integrate, use calculus, and get the answer between two endpoints. So let's have a look at our last example, which was the parabola. The equation was v equals t squared. The distance travelled during the time t equals 0 to t equals 2 can be found by the definite integral. This is saying anti-differentiate between t squared between 0 and t with respect to t, which is just a fancy way of saying tell me the area under the graph between 0 and 2. When we anti-differentiate t squared, we get 1/3 t cubed. We've got to work out the answer between 0 and 2. So I substitute 2 in and I'll get 8/3. Substitute 0 in and I'll get 0/3. So that means 8/3 meters. By using calculus and anti-differentiation, we can integrate and find out the distance travelled from a velocity time graph. But this is just an example, of course, of the area under the graph being something useful that we can work out.